So I would like to thank also the organizing committee for giving me this opportunity. Basically, first I would like to complain to our younger. So I can see the population here. So it's mostly like half of population of male and female. But if you look, so 4 of us came from IIT Ropar, but 3 of them are male and I am the only female. So I don't know what happened. So until masters, so I did my masters from Kurukshetra University. So there also the population of female was quite a lot. But then when I look at the higher studies, so there are not many female. So I would be very happy when next time I come here, so I should be accompanied by female faculty. So that would be great if we can do that in coming years. So with that, so I would like to start my talk. Basically, I will be talking about the quantum materials, so which Dr. Lakhan has already talked about. But he was, so most of my colleagues, they were discussing everything in the nano world. But before going to nano world, you need the bulk material, right? So then only you can, do some process and you can bring them down to the nano level. So you need bulk material first of all. Okay. So that is the one aspect I will be talking about. And why quantum materials? So these are the materials whose physical properties cannot be described by the normal classical mechanics. So you need quantum mechanics to explain those phenomena. Okay. So most of all, I think you don't like quantum mechanics at this level. This I can understand because I can relate to you. When I was in my masters, I was just hating quantum mechanics. But most of the fascinating materials in our real world can be only explained through the quantum mechanics. Okay. So the very first material I will be kind of discussing is superconductivity. Okay. So most of all you are already familiar with the superconductivity topic, I believe. So basically superconductivity was discovered in 1911 by Dutch physicist Kamerlingh Onnes. Okay. For that he got a Nobel Prize in 1930. Okay. So most of the remarkable phenomena you see around in your world is a result of a coincident experiment. For example, Dr. Vijay was explaining about the graphene, right? So you all know that was a purely coincidence event that happened. So basically somebody kind of was just sharpening their pencil, the scientists who discovered this phenomena. So basically they were sharpening their pencil and then that whatever came out from the pencil, so it just kind of thought of doing a experiment, so measuring the electrical conductivity of that particular thing. And they came out that the electrical conductivity is much higher than the normal metal. And that's how all the other experiments started with that material. Okay. So here superconductivity also was a result of coincident experiment. So basically what Kamerlingh Onnes was doing, so they were trying to re-liquefy helium in their lab. So they succeed with that experiment. So basically helium, before that it was only gas which was existing. They try to re-liquefy it and then people can reach down to 4.2 Kelvin. Okay, so 4.2 Kelvin is the liquefaction temperature of the helium. Okay, so basically this low temperature opens up quite a new world. So whatever quantum mechanics or whatever quantum we are talking today, it's just because we can reach down to the low temperature. Okay, so at that time he thought maybe I should measure some conductivity of a mercury wire. Okay, so he just measured the conductivity of that mercury wire and he came to know that suddenly below certain temperature, which is 4.2 Kelvin, the resistance suddenly goes close to zero. Okay. So this was how the superconductivity was discovered. Okay, so superconductivity was there, but then there was no explanation why it exists. So also they did one more experiment. So they just kind of flow a current through that mercury loop, and they found out that that current persists. So it stays for very long time. So you know, in normal conductor, if you try to flow the current, there is a resistance, right? So that resistance will not allow that current to, flow forever. But there is certainly something interesting happening in this system, this kind of system. So, but there was no explanation. Okay, so what Dr. Vivek was saying in the morning talk, that you need first theory and then experiment will follow. I will say vice versa here, because experiment was existing, but there was no explanation why this is going on in this system. Okay, so until 1920, so there was almost a decade that superconductivity was discovered, but there was no explanation because there was no quantum mechanics up to that time. Okay, so you know, Schrodinger equation, then Heisenberg picture, they all kind of started showing up in 1920s. So only by then scientists started thinking about the explanation for the superconductivity. Okay, so why we need explanation? Because of course if we want to go to higher temperature, because of course for the real world we cannot work in low temperature range, right? You cannot afford liquid helium every time. It's very, very extremely expensive. So even in our lab experiment we cannot afford that. Okay, so that's why you need to go to high temperature, but to go to higher temperature you need to understand the physics at lower temperature, right? So until 1920 there was no quantum mechanics, so that's why nothing happened for a decade. But then as soon as quantum mechanics came into picture, Schrodinger equation and then Heisenberg picture, so then there was London theory. Bullet train to India, bullet train to India. So these bullet trains basically, they are all kind of work on the principle of the imaginary force. Okay, so you know why these bullet trains can travel faster? Because there is no resistance. So they are made up of the superconducting material. Okay, so there is no exact, because the magnetic field will expel the magnetic flux from the interior of the superconductor. So there is no direct contact between the train line and the train. So as there is no real contact between the two, so of course the resistance is less, so train will go with a very high speed. So that's the concept of bullet train. So that was the phenomena explained by Meissner and known as Meissner effect. And then the real theory which could explain superconductivity was the BCS theory of superconductivity. So where you can see three scientists, Barden, Cooper and Seifer, they came up with a theory. And I must tell you, before that also Barden, I don't know if you have heard about Barden, except from the superconductivity. So he discovered transistor, right? So he was the co-investigator of the transistor. Okay. So basically at that time, 1920s also, he was trying to look for the physics behind the superconductivity, but he could not succeed. But in 1957, along with these two gentlemen, they came up with a theory, and which says that the electrons, they are not traveling alone, but they are traveling in a pair. Okay. So for example, there is one electron which passes through the lattice and it polarizes that lattice, and that polarization is then experienced by the second electron. So basically the second electron will feel less resistance. So maybe I can give you one example, since we are in the hilly area. So you must have experienced snow in your lifetime, of course. So if there is a fresh snow, okay, and if one person is traveling through that snow, so of course he won't be able to travel much. There will be quite a lot of resistance. But as soon as second person comes into picture, that person will feel less resistance, right? And as soon as many people have crossed that path, after that the path becomes very easy and there is no resistance at all from the snow, it becomes ice, right? So that's the same explanation what Barden, Cooper and Cypher gave. Okay? So this was the very first explanation which could explain many of the phenomena of superconductivity. And because of that, they got Nobel Prize in 1972. Then there was another theory. There was Josephson-Johnson explained, and they got Nobel Prize in 1973. So, if you look at the history of the superconductivity, so before 1940 there were only elemental superconductors existing. What do you mean by elemental? So there is one single element. Okay. So Tc was also very, very small. It was almost in the range of 3-4 Kelvin. But then there were also some compound superconductors. You can see niobium-3, niobium-Ti, and some more. But the Tc was staying at very low value. But if you look at 1986 year of the time, so there you see there is a sudden jump in Tc. So these are the cuprate based superconductor. So you can see the Tc, one can go up to 140 Kelvin, which is quite high. And for that cuprate based superconductor, there was another Nobel Prize given in 1986. So then there is one more Nobel Prize in 2003 in the same field, but there they explain the superfluidity. So after that there is not much actually beside the iron-based superconductors. So where iron is present, but still superconductivity is there. Okay. So we all understand that when Cooper pairs are formed, so they kind of try to align in different directions of the scale. Okay. But what is going on with the iron-based superconductor? Since there is iron, so magnetism is thought of enemy of the superconductivity. So there is something different going on beside the BCS theory of superconductivity. So BCS theory, which was given in 1957, could not explain this phenomena. Then there are many theories, and this field is still kind of going on. Okay. So you can see so far we have reached up to 270, 280 in this halide. So these halides LaH10 and H2S, but that too at very, very high pressure. So the pressure here you can see is 170 GPa. So in your lab you apply such a high pressure, then you can go up to almost room temperature superconductivity. But if you look at the pressure value, this is almost close to the core pressure of Earth. So you cannot, use that pressure in your real world. It is not possible. Physically, it is not possible. So that means you need superconductors at room temperature. That is the next. If somebody discovers that, so that is the next Nobel Prize for sure. But as I said, to go to room temperature, you need to understand the existing material at room temperature, at low temperature. Okay. So this is what actually one of my areas. So I try to look at different kind of materials, their superconductivity, and then to see how the electrons are pairing themselves to make the Cooper pairs. So this is one of the research area I am working. And then as I said, I work on the growth of the bulk sample through which one can go to the nano level. And so understanding the gap symmetry means how the electrons are paired. So for example, you have a Cooper pair and you need some energy to break that Cooper pair, right? So that Cooper pair will then become a free electron. So that amount you need to break that Cooper pair is known as the gap value for that superconductor. Okay. So whether that gap is isotropic over the Fermi surface or it is anisotropic, whether that gap vanishes in some direction of the Fermi surface. So that thing will help us to understand the superconductors well, and maybe in future we can apply the same theory to some other kind of material, and eventually one can get, as I said, any invention is the result of coincidence most of the times. Okay? So then next is there are some certain materials. So for example, for superconductivity you need Cooper pairs, right? And if there is a material, there are two phenomena occurring in the same material. So some of the electrons are kind of taken by the other phenomena, and some of the electrons are taken by the superconductivity. Then of course Tc will be low in that material, right? Because there are not many Cooper pairs there. So you need to, first you need to get rid of that phenomena which is competing with the superconductivity. Okay. So this is one of the topic I will be discussing. So you need, so just to get rid of that phenomena, you need some tuning parameter. Either you apply pressure or you kind of dope that system. So these kind of thing, and then van der Waals materials. So basically this topic I think is already being discussed many times. So again I grow the bulk of this material, and then these materials can be peeled off just like onion. So you just peel off, because the interlayer strength is very weak in this material. So among the layer this is covalent bonding, and between the layer it is the van der Waals bonding. So that's why the layers can be easily peeled off, and then you can use those layers for any of the device applications. So this is one of the area I am working on. Then comes the altermagnets. So basically many of us have heard about only diamagnet, paramagnet, ferromagnet and antiferromagnet and ferrimagnet. So these 5 states of magnetism, right? So this is a new phase which is discovered very recently, and where it is useful. So as Dr. Lakhan was explaining in the spintronic devices, you need to have some spin dynamics in that system, but if you look from the outside, there should not be any magnetic field, there should not be any stray field, for example. For example, you in your phone, if you are using that device, whichever is made by, for example, Dr. Lakhan, so there should not be any stray field, right? If there is a field, then that field will interact with the field from the outside world, and then your electronics, whatever is there inside your mobile, won't work the way they should be, right? So that means you don't need any stray field. That's why ferromagnets are not good for the spintonic device application. You need antiferromagnet. Then antiferromagnet, they are like spins are anti-parallel to each other. They give almost zero magnetization. So you cannot, use the spin dynamics because there is net magnetization is zero. But what happens in these altermagnets, that from outside if you look, so they are like giving you zero stray field, but inside there is some magnetization dynamics. So they can, completely change the spintonic devices which people are kind of looking at right now. Okay. So these are some of the fields I am looking at. So I just want to mention about the charge density wave. So this basically is a phenomena which competes with superconductivity. So in many material where you see very high superconductive transition, that superconductive transition was achieved once this charge density wave was suppressed. Okay. So what is the charge density wave? As the name suggests, so there is a density of charges. So it's not like the charges are uniform, but they are periodically modulated. Okay. So for example, if you look here in figure A, so this is at room temperature. Okay. So there you look at simple EK diagram. So you have brilliant zone boundaries at minus pi by A, plus pi by A, and if you look, so atoms are equally spaced with the lattice spacing of A. Okay. And the straight line over there is the electronic charge density, which is uniform all over the space, right? Because the atoms are equally spaced. So there is no change in the electronic charge density. And the red line here shows that up to this level the electronic states are filled. Okay. So there is no gap because we are not yet reached to the billion zone boundaries. But what happens below a certain temperature, the lattice modulates itself. So basically now the atoms are not equispaced, but they form a pair like this. Okay. So before the spacing was A, but now it becomes 2A. Okay. So there will be new billion zone boundaries, and those billion zone boundaries will be minus pi by 2A and plus pi by 2A. So those billion zone boundaries will now lie inside the occupied electronic state, and there we all know at the billion zone boundary what happens. So if a wave is coming, so it reflected back and it gives you a stationary wave, right? So there is a opening of the gap at the billion zone boundary. This is what is happening whenever you have a charge density wave in your system. So basically, so there is a partial opening of a gap at the Fermi surface. So you basically, some of the charge carriers are not participating in the conduction. Okay, this is what you mean when you have gap at the Fermi surface. Okay, so now that means this phase will be competing with the superconductivity, because for the superconductivity you won't have many charges, many electrons in your system, right? So Tc will be low, but once somehow if you can suppress this charge density wave, you can get very high Tc. Okay, so this is one of the phenomena I will talk about today. So these are I chose this material AV3SP5, which has a Kagome lattice. Okay, so this material actually I chose because it shows superconductivity along with the charge density wave I just described. So basically what Kagome means, so this is a very popular actually area right now. So many interesting physical phenomena is happening in these kind of materials. So Kagome means a basket. Okay, a basket in the Japanese. Actually, this is a Japanese term which means basket. Okay, so I have shown also a basket here. So you can see a basket. And if you look at the crystal structure of this material, these type of material, they exactly look like this basket. Okay. So we have a Kagome network of vanadium cations, which is coordinated by the octahedra of antimony. Okay. And because of this type of very interesting crystal structure, if you look at the Fermi, look at the density of state, so you can see there are some flat bands here, and then there is this linear band crossing. Okay? So whenever there is a linear type of band crossing, the conductivity becomes extremely high. And these are not the trivial features in any compound. They are non-trivial. They are very interesting. So basically, these type of material, they show charge density wave along with superconductivity, and then these non-trivial features in their band structure. So that's why these materials are really interesting. So first of all, we'll try to look at the gap symmetry of these materials at the ambient pressure, and then what happens under pressure, whether we are able to suppress the charge density wave and get the Tc high or not. Okay, so that we want to see. Okay, so this is the ARPUS picture, which is the real experiment where you can see clearly this linear crossing of the bands. Okay, so to probe the superconductivity. Okay, so for example, if you want to look at the magnetization of any material, so you will put that material inside a magnetic field, and then you will probe the magnetization of that material, right? In case of superconductor, what one will do, we want to look at the vortex state of that material, right? What happens, so you have two types of superconductor, type 1 and type 2. So in type 1, there is a upper critical field above which the material becomes completely normal, But in type 2 superconductor, what happens? There are two critical fields. Below lower critical field, the material is completely in Meissner state, and between the two upper critical fields, there is a vortex state. So the vortex is kind of, there are some regions where you have magnetic field, there are some regions where you have normal state. So it's kind of a mixed state. Okay. So you want to probe that mixed state, and what we did, we use muon. Okay. So muon is a spin half particle. It can have a positive charge or negative charge. So we use positive charge muon with spin half, and we use 100% spin polarizing muon. So whatever the spin we have used, it was pointing along one direction only. So there was not that if you have taken 100 spins, so some of them are pointing up, some of them are pointing down. So all of them were pointing in the same direction. Okay. So why muon? Because if you look at the gyromagnetic ratio of the muon, it is quite high. So if there is a quite high gyromagnetic ratio, that means you can probe even a tiny magnetic field of any material. Okay. So if there is a vortex state in a superconductor, so you can probe that vortex state using the muons. Okay. So what normally muon is? So muon has a lifetime of 2.2 microsecond, and after that 2.2 microsecond, it decays into a positron, and then some neutrino and antineutrino. Okay. And this is a three-body decay, so it is a kind of weak decay. Okay. And since this is a weak decay, there will be a parity violation, and because of that parity violation, the positron which are emitted from the muon decay will be emitted anisotropically all over the solid angle. Okay, and that anisotropy one has to measure. So if we measure, so these things I am not going into much detail. Also, if you look at the muon spin at any point of time, so this will be along the direction of the positron emission at that particular point of time. So that means by looking at the spatial positron emission as a function of time, you can basically probe the spin of the muon as a function of time. Okay, so this is what this experiment does. So basically these are the number of positrons which are collected on a detector. Okay, so you basically sign your sample with the muon beam, and then you will have positrons, and those positrons are basically detected. Okay, and these positrons basically they compromises of this background term. Then you have a decay term from the muon decay, and then in the bracket you have this term PT, which is the spin muon spin polarization, and N is the direction in which we are looking, in which our detector is placed. Okay? So this basically this kind of spectra you will get out of this experiment, and this spectra which is showing muon spin polarization as a function of time. So why there are oscillations? Because you apply a magnetic field from outside. Okay, so then muon spin will presses around that magnetic field, and the oscillation frequency is giving you the magnetic field. Okay, so the frequency will give you the value of the field which is experienced by the muon, and the decay of that signal will provide you about the field distribution, or how the, like for example, if you have a normal material, so what you will see, if you take the Fourier transform of this spectra, so there is some broadening in this spectrum. Okay, so if you have a normal material, there is no field distribution, you apply a magnetic field from outside, you will see a single peak. Whatever the field you are applying, you will see a peak corresponding to that only. Okay, but the field is, if the field inside that material is inhomogeneous, so you will see not the single peak but a broadening in that peak. Okay, so that broadening is basically giving you the field distribution inside, for example, superconductor. In a superconductor, the field dynamics is not very uniform because at some places you have magnetic field, at some places you have normal matter. So basically these are some of the property you can study if you have a magnetic sample, and in case of superconductivity you can determine the penetration depth, how much the magnetic field is penetrating inside the superconductor, the coherence length, and the vortex dynamics. Okay, how the vortices are formed, whether they are triangular in shape, whether they are hexagonal in shape. So that kind of vortex dynamics you can study, and also you can determine the symmetry of the superconducting gap function. Okay, so these are some of the things you can basically study using the Bion only. Okay. So now coming back to the material which we started talking about. So this material actually it is grown in the lab. You can see you remember it has a hexagonal type of structure, and if you look at the crystal which is shown in the first picture, so this is the optical picture just taken by a camera on a millimeter scale paper. So you can see a clear hexagonal symmetry of that crystal, and you see how beautiful the crystal is looking. Okay, and the second picture is the Lave picture. So where again this is one of the methods to determine the symmetry of any crystal. So you can see clear hexagonal symmetry there also. Then the third picture is the XRD. So basically you all know how to do, like at least theoretically you know how to perform X-ray diffraction, Bragg's law, right? So whenever the Bragg's condition is satisfied, you will have a peak in your spectrum. Okay. So but here if you look at the peaks, so these peaks are along 001, 002, 003. Okay. So these are not the peaks like 110, 100. You are only getting certain peaks. Okay. So this is 00L planes you are getting. That means your crystal is oriented along C-axis. Okay. So the perpendicular to that crystal is the C-axis, and the inside the plane is the AB plane. Okay. So this is what this XRD is telling you, and also you can see there is no additional peak, nothing, which shows that this crystal is very pure. Okay. Then you do the magnetization measurement. So pi versus T. So you have heard about the superconductor is perfect diamagnetic material. So this is clearly visible from here. So you can see this is going in the pi versus T is in the negative direction, below 2.5 Kelvin. Okay, and you can also look at the resistivity here, which goes down almost to 0, below 2.5 Kelvin. So it has a TC of 2.5 Kelvin, and there is a charge density wave transition at around 94 Kelvin, which can be seen also with certain features here. Okay. So now we want to probe the gap symmetry of this compound. So as I said, so you see there is a muon spin, so muon with a spin coming there, and then you have 4 detectors, and there in the middle is your sample. Okay, and you apply external magnetic field, and then this muon spin will start precessing around that magnetic field, and what you will get, this type of spectra. So I already told you from this spectra what kind of information you can get. So just looking at the oscillation frequency, you can determine the magnetic field in that particular sample, and by looking at the damping of that signal, you can tell something about how the vortices are distributed inside the superconductor. Okay, so you can see the first spectra is at 5 Kelvin. So there you see the damping is very weak, but as soon as you go inside the superconducting state at 0.27 Kelvin, so you have basically a very strong damping. This is because now the muon is experiencing different field. So you can see from this picture, I don't know if this is clear to you. So muon can stop between the three, so these are the vortices I have shown here in the picture. So muon can in principle stop here, or it can stop in between the two vortices, or it can stop inside the vortices. Okay. So if you take the Fourier spectra of this asymmetry versus time spectra, so you can see this cutoff at the lower field is because of the muon stopping between the three vortices, and this peak is because of the muon stopping between the two vortices, and this peak is because of the muon stopping inside the vortices because this has the highest field, and then the tail at the higher field is because of the muon stopping between the two vortices. Okay. So from this broadening of the field distribution, so this broadening is basically directly proportional to the inverse square magnetic penetration value. Okay. So this spectra is then fitted with some skewed Gaussian. So this is not the perfect Gaussian, but it is a skewed Gaussian type spectra. So after that fitting, we got certain parameters, but what is important is this internal magnetic field, which is at the muon side. So you can see there is a drop in the magnetic field experienced by the muon. This is because of the diamagnetic shift inside the superconducting state. And also one of the parameter is this skewness parameter. So this skewness parameter, if this is greater than 1 or close to 1, that means your vortices are very rigid inside your material, and if this is less than 1, that means your vortices are not stable, they are flowing inside your material. Okay, so this is one information given by this skewness parameter. Then we try to calculate this inverse square magnetic penetration depth, and we fitted this data with different models for the gap symmetry. So one of them was S-wave symmetry, where the gap is isotropic over the surface, or D-wave, where you have nodes at some point, and also you might have two gaps opening at different parts of the surface. That can also happen. Okay, so this is exactly what is happening here in this compound. So you have a multi-gap scenario in this compound. This is what we kind of estimated from the ambient pressure measurement. Now what happens when we go to pressure? So I will not go into much detail about what was reported before. Just let us go to the results what we get. So this is how you basically apply pressure. These are some of the tools we use to apply pressure on any sample. Okay? So this is the result actually we got. So you can see, so high temperature experiment I am not showing here, but you see at 0 GPa, the GPa means the gigapascal pressure I am talking about. So the TC was 2.5, but as soon as you keep on increasing the pressure, what happens? At around 1.74 GPa, your TC suddenly goes from 2.5 to 8 Kelvin. So it's like almost threefold increase in TC. Okay, and what happens exactly at this pressure? So the charge order which was present at high temperature, it got stressed. Okay, so just because that charge order is not anymore, so that means there are more electrons which is available for superconductivity, right? There will be more Cooper pairs, and that's why the TC is increased. Okay, so this is one way to increase TC. So this is the way actually people are kind of doing in many materials to increase the TC, just to suppress the competing phase from that material. Okay, and then these are some more results, but I think I will not go into details of those. Okay. So So then the next one is just to know what is the nature of the charge order phase which is present at the high temperature. We also did some DFT calculation. Of course, we had experiments in hand. Then we needed theory people to explain our result. That's where the DFT comes into picture to understand the result you are getting. Okay? So we understood that the charge order phase is a star of David phase, which I think is fine. I will tell about that. So again, one of the very important experiment is like instead of applying, so for previous experiments you were applying some external field from outside, okay? But what if you don't apply any magnetic field? So what will happen in a case of superconductor? If it is a conventional superconductor which is following the BCS theory, so BCS theory says that the Cooper pair, the two Cooper pairs, the electrons forming the Cooper pair should have opposite spins, right? So if you look at the net magnetization, it should come to 0, right? So if you are not applying any magnetic field from outside, and if within the superconductor also there is no field, so you should not see any change across TC. Okay? But what if you have, instead of having the opposite spin electrons which are forming the Cooper pair, if you have Cooper pair which have the same direction of the spin, in that case there will be some magnetization coming from the superconductor itself, and that can be also probed using this technique. So you can see the change across TC here, and this is showing that there is some internal magnetic field present in the system because of some unconventional pairing of the Cooper pairs. Okay? So in principle, by using this technique, we can study most of the things about the superconductors. Okay? So these are some in the same category.